On to chapter 6 with chapter 16 with a chemical equilibrium. So hemoglobin is a protein that helps carry oxygen to cells. And there are four sites where the oxygen can join. And hemoglobin plus oxygen is in equilibrium with the hemoglobin oxygenated complex. This is known as a dynamic equilibrium. But it also has to be easily to pop off the oxygen, otherwise it wouldn't be able to transport the oxygen. That's why this needs to be in equilibrium. So, and the concentrations of each of the reactants and products, these are interdependent. So, and the relative amounts of these is called the equilibrium constant. A very large equilibrium constant means lots of products. A very low equilibrium constant means lots of reactants, and one about like in the middle, around one or so is about equal reactants and products. But the shifts and equilibrium, that's what we're going to talk about in this chapter, and how the concentration of things affect the equilibrium. So with oxygen, you have a high amount of oxygen in the lungs, and this shifts the reaction to the right. And then when you transport it to your cells, there's less oxygen in your cells, and the reaction shifts to the left, and then the oxygen pops off. And fetal hemoglobin, it's higher than an adult. So that means it's more effective at binding oxygen. This is important so that oxygen can be bound and brought away from the mother, because the fetus can't, well, it can breathe, but it can't take in fresh air, fresh oxygen when it's in utero. So this has to come from the mother, and then the binding needs to be stronger in the fetal hemoglobin so that the reaction will shift further to absorb oxygen away from the mother. And this oxygen exchange happens at the placenta. And with chemical reactions, reactants are consumed, products are generated, and generally as the reaction proceeds, assuming it's a closed system, the reactants decrease and the products increase in concentration. But as the concentration of the reactants decrease, the reaction rate of the reaction decreases. And eventually the reaction reaches a state where the rate of the reaction forward is the same as the rate of the reaction the other way, and the backwards. And this only works, of course, for reversible reactions. Some reactions are not reversible. So burning of like your chemistry textbook, if you have a paper copy, that's an irreversible reaction, only goes one way. But for simple reactions, these can go both ways. And then when this looks like it no longer changes, you've reached equilibrium. So the dynamic equilibrium, this is where the reaction rates forward and backwards are equal. And then it looks like nothing is happening, but there's stuff happening. Things are being broken apart, things are being formed. And so if you look at this, for instance, if you have hydrogen and iodine make hydrogen iodide, or two hydrogen iodides, initially just having reactants, then as the reaction goes, and eventually you get to a point where the reaction reaches equilibrium, where the forward rate is the same as the reverse rate. And this is equilibrium. But it doesn't mean that it stops happening. So here at the dynamic equilibrium, here's another picture. So the y-axis shows the concentration, x-axis is time. Just like the other images, you have a higher concentration of reactants and no products. The reaction shifts right and it goes forward. Eventually, the concentration of the reactants and products don't change. That doesn't mean there's nothing going on. There's actually a chemical reaction going on, but it's just the overall chemical reaction. It doesn't, the concentrations don't change. And then, like I said before, this is known as the dynamic equilibrium. So equilibrium does not mean equal. So then it just depends on the equilibrium. So it depends on the value. We'll talk about this soon, the value of K. Some equilibrium happens Well, some of them are about even. Uh, Most tend not to be. Either way, one way or the other. The products are favored or reactants are favored. It just depends. Depends on the reaction, depends on the conditions. So, analogy for this. So, imagine you have country A, country B, lots of people in country A, and a few people in country B. What's going to happen? So, more people are going to kind of move to country B. But eventually, which is an equilibrium, where the number that are leaving A is the same as the what are being number of people that are moving from B to A, and that's so that doesn't mean that people aren't leaving and coming in. It just means that they're about the same, and that's the same idea with equilibrium. So, which statement does not generally apply to chemical reaction in dynamic equilibrium? The concentration of reactants are equal. This is not necessarily, it can be true, but it's not necessarily true. So the equilibrium constants, there is a relationship between them, and the relationship between them, the reactants and the products, is called the law of mass action. So the most general equation, uh, little a of species big A, little b of species big B is an equilibrium with little c of big C and little d of species D. So C and D are products and A and B are reactants. And there's the law of mass reaction shown below. The equilibrium constant is the concentration of the products raised their coefficients divided by by the concentration of the reactants raised their coefficients in the denominator. So and these are all at equilibrium, and this is known as the equilibrium constant. So which one of these? So if you have 2a plus b in equilibrium with 3c, which one is it? It's the product c cubed all over concentration of a squared times concentration of b in the denominator. So for this reaction here, you have 2N2O5 in equilibrium with 4NO2 and O2. You have the expression, so over the products, NO2 to the fourth, because there's a 4 in front of the NO2, times concentration of oxygen, divided by the reactant N2O5 squared. So what is the value of K? For a very large value of K, it means that the reaction shifts mostly to the right, favoring products. For a very small value of K, means the reaction tends to stay left or favors the reactants. And so formation of HBr from hydrogen and bromine, this is an example of a very large number, very large K. This reaction goes almost to completion. Many complexes we'll learn later that's like, so when you get ligand formations, these can be very, very far to the right. Some things that are very small. So here you have nitrogen plus oxygen reacting to form 2 nitrogen monoxides. This is a very small number. So nitrogen oxygen tend to be in the air. There's very little nitrogen monoxide in the air right now. So this means this reaction doesn't proceed very far. We'll find out soon. Acids and base dissociations for weak acids and weak bases. These tend to be very small, so this is going to be important for future chapters. So consider this reaction A in equilibrium with B. The images shown here illustrate the equilibrium mixtures of A, red, and B, black, at 3 different temperatures. At which temperature is the equilibrium constant the largest? That means there's lots of B over a little bit of A, so B is black, so the one that has the most black over the fewest red, and it's that one. Relationships between equilibrium constant and chemical equations. Well, so if you reverse the equation, you flip K. So the backwards reaction is 1 over the original K. And the reason for that is because the reaction is products over reactants. So if you flip it, then you put reactants on top, so you're flipping K. So for coefficients, if you double a reaction, you have to square it, the K. So whenever you multiply K by some factor, you raise the new K by that same factor. And when you add equations to get a new equation, it's the equilibrium constant of the new equation is the product of equilibrium constants from old reactions. So if your reaction's A in equilibrium with B and B in equilibrium with C, for A in equilibrium with C, you take the two equilibrium constants and you multiply them together. You can also see that the B cancels out in that. So for equilibrium constants for revolving gases, instead of concentration, you can use pressure. It's the same idea. The difference is instead of a Kc, Kc is for concentration. If you don't see the C equilibrium constant, usually the K just means Kc. Then instead the Kp, that the P is for pressure. And the way that you can transfer if you have Kp or Kc and you want Kp or Kc from the other, you can find it by Kp equals Kc times the quantity RT raised to the change in N. N is the number of moles that are changed. So the final moles minus the initial moles of gas. So that is how you do that. So for how to derive this, here is part of the derivation right there. And here is the rest of the derivation to show the relation between Kp and Kc. So under which circumstances are Kp and Kc equal for the reaction shown here? And that's for when the change of N is 0, because RT, anything raised to the 0 power is 1, well, except for infinity or 0. But that's for higher level math, of course. But anything raised to the 0 power is 1, so Kp equals Kc. So for heterogeneous equilibrium, so different states, so concentrations of solids and liquids don't change. So what is the concentration of a dust particle of calcium carbonate chalk versus an entire mountain of it? What's in concentration is amount per volume, and the amount per volume doesn't change. And so because of that, solids and liquids are not included in the equilibrium constants. So they are not included in equilibrium expressions at all. So other things, so if you see here, 2 carbon monoxide, equilibrium carbon dioxide, and carbon, the amount of carbon is different, but the amounts of carbon monoxide and carbon dioxide remain the same. So the amount of carbon has no effect on the equilibrium. So that's one other thing with solids. They just as long as they're there, it doesn't matter really how much you have. Of course, this is not necessarily for rate and time. If you are doing something like burning things, of course the amount of fuel matters, but this is just dealing with the equilibrium. So for which reaction is Kp equals Kc, so it's the one where the moles of gases are the same on both sides of the equation, and the one is B, that has the one that has the same number of moles of gas on both sides of the equation. So how do you calculate them? The most direct way of finding the equilibrium constant is to measure this stuff and then put it in to and when it reaches equilibrium, and then calculate the equilibrium constant. So it doesn't matter how much you have initially. The equilibrium constant is independent of how much stuff you have initially. It's after a long time. A temperature, it does depend on temperature. So here's an example of this. So initial conditions and equilibrium concentrations, and you can see that it doesn't matter what you start off with, the equilibrium constant is always the same, hence the word constant, at a specific temperature. So you can use stoichiometry to determine the equilibrium concentrations if you know the initial concentration and one equilibrium concentration. So this is just using the degrees of freedom. So if you have one unknown, you need one equation. So keep that in mind with this. So set up an ICE table. ICE stands for initial change in equilibrium. So initial change in equilibrium, and then you fill in the table, and then you go from there. So reaction quotient. So at any given time, so Q equals K at equilibrium. But at any given time, we have a reaction quotient. And then you can compare Q to K and see where it needs to go. It tells you which way the reaction is going to shift. So for this gas phase reaction, A of A plus B of B in equilibrium with C of C and D of D. So we have the reaction quotients and concentration and pressure as follows. So when Q is smaller than K, that means that, so if Q is small, that means the top number is too small and the bottom number is too big, so in the numerator denominator. So that means that the top number needs to get bigger and the bottom number needs to get smaller. Therefore, the reaction shifts right towards the products. If Q is greater than K, that means that the top number is too big and the bottom number is too small. So that means the top number needs to get small and the bottom number gets bigger. That means shift towards reactants. So that's actually how I remember. I don't have this memorized. I've reasoned through it every time. And, well, I've already mentioned that. So at equilibrium, Q and K is the same. And then the overall concentration of products and reactants will not change. So, and this is summarizing the direction of change, what we talk about with the chart. For the reaction N2O4 in equilibrium with 2NO2, reaction mixture at a certain temperature initially contains both N2O4 and NO2 in their standard states. If Kp is equal to 0.15, which statement is true of the reaction mixture before an equilibrium occurs? So this means that Q, if K is 0.15, Q is going to be 1, and that means Q is greater than K, which means there's too many products and too few reactants, therefore we'll shift left. So how do you find equilibrium concentration given K an initial concentration of pressures? Prepare the initial change equilibrium table, the ICE table. Decide which direction the reaction will proceed. It's very easy if there is a 0. You will shift towards a 0. If there is a 0 on both sides of the equation, the reaction just won't go. So there needs to be complete products or reactants for the reaction to happen forward or backwards. Determine the changes in terms of x, the extent of a reaction, and then look at the stoichiometry to know how many x's, like if it's 1 or 2x or that kind of thing. So positive change means generation, negative change means consumption. And solve for that extent of reaction. So there's a way to simplify the math. If you have a value, and if that value is being related plus or minus to x, if that value is much larger than the value of that x, you can approximate by discounting that x. So, and depends on what the approximation is, and generally speaking for this class, it's about 5%. And it really just depends on what you're doing. So, if you are doing something like the deep impact probe, or you are taking something and shooting a satellite towards a meteor or comet, and you need to hit that meteor or comet, you need to be very, very precise in terms of your mathematics. If you have a pH probe in the air, this pH probe is 10%, and you're doing calculations to support that, an error of 5% is fine. So it really just depends on your circumstance when you can and can't discount x. So for this generic reaction, A in equilibrium with B, consider the value of K as initial concentration of A, the reactant. For which value of which set of values does x-small approximation likely apply? And it would be the first one, where A is big and the equilibrium constant is small. So also, when equilibrium is disturbed, the system, if a system is in equilibrium and equilibrium is disturbed, the system will shift to go back towards equilibrium. And the concentration can be different, but the equilibrium constant is the same. Unless the temperature changes, then the equilibrium constant will change. So this is known as Le Chatelier's principle, and this is a very important thing. It's actually a very simple, but it's a very powerful tool. So I recommend you think of this and then you use it in future classes. So, and it says a system equilibrium is disturbed. The equilibrium, there will be a shift to minimize the disturbance and go back to equilibrium. And the disturbances, they include changing concentration of reactant or product, changing the volume of the pressure, or changing the temperature. So these are the types of things. And changing the concentration of reactant or product, that means you can add it or remove it. So that's an example of that. So analogy to population changes. So remember, you have country A, country B in equilibrium, and the rates are equal, so the population stay constant. So that means what happens if you suddenly have a huge birth rate, a baby boom in country A, it disturbs equilibrium, and then because of that, you'll have more migration to A to counteract that shift in equilibrium. So adding a reactant, if you add a reactant to the system, as long as it's included in the equilibrium constant. So I mean, if it's not a liquid or solid, because those concentrations are constant. So does this affect the forward reaction, or does it affect the reverse reaction? How does it affect the value of K? It doesn't. The answer is it doesn't. As long as the temperature doesn't change, the equilibrium constant doesn't change. But adding a reactant to the system, you shift to the right. You shift towards products. So, and as I mentioned here, this causes a shift to the right. So removing a reactant, removing the reactant is what's going to happen. The value of K still does not change. You shift left towards the reactant. So removing reactant, that means the system wants to make more. So then the equilibrium shifts left to generate more of that which you've taken away. So in general, adding a reactant will have a shift to the right, and removing a product will also have a shift to the right. So if you add a reactant, the system wants to get rid of that reactant, which means the reactant will go forward. If you move a product, the system wants to generate more product, so you shift right to generate more of that. So and generally speaking, the equilibrium shifts away from the side that is added chemicals, and you shift towards the side where it removes. So this only applies for things that are not solids or liquids. So here is Le Chatelier's principle showing changing concentration. If you add NO2 product, the system shifts left and generates more N2O4 reactants. And there's a system at equilibrium. The system is shifted, and now the equilibrium will then return, will reestablish itself. And then after the equilibrium is reestablished, the equilibrium constant is now, it's not the same. Although the reaction concentrations, the concentrations are different than the original, but the equilibrium constant is the same. So what about changing the volume? So changing the volume, I tend to think of it in terms of pressure. Well, if you change the volume, the system, the volume going down is the same thing as pressure going up, and the volume going up is the same thing as pressure going down. And adding, in that case, decreasing the volume will increase the pressure, and the system wants to shift away from the pressure. So what's it going to do? It's going to shift towards a side that has fewer moles of gases. So it's going to try and shrink, if you will. So decreasing the volume, the system is going to try and actually shrink. It's going to try and be more compact, and it's going to also make the system that makes the pressure go down. And decreasing the volume, you go in the direction that has a fewer mole of gases. Increasing the volume goes the other way around. The number of moles of gases goes towards shifts towards the side that has the higher moles of gases. Of course, if you have the same number of moles of gases on both sides of the chemical equation, then absolutely nothing happens. So what about adding an inert gas? That has the same thing as increasing the pressure. So it has no effect on equilibrium, but it increases the pressure. So, and for aqueous systems, there's no effect on the equilibrium because liquids are considered incompressible. So, adding a gas to a gas phase reaction, if it's a reactant, you shift right. And if it increases the partial pressure, it's the increases the concentration. That depends on the circumstance. So and adding in their gases, they do absolutely nothing because then it's not going to change the relative partial pressure. Oh, that makes sense. So volume changes. So increase in pressure is the same thing as decreasing the volume. You shift towards the side of the lowest number of moles. Increasing the volume, decreasing the pressure, you shift towards the lowest number of moles. And so it just depends on the context. You have to count the moles of the reactants and the products. So the effective temperature changes in equilibrium position. So exothermic reactions that release energy, it's as if energy is a product. Endothermic reactions absorb energy. It's as if energy is a reactant. So it depends on which side in this. So if for an exothermic reaction, heat is a product. So adding heat to a reaction is adding a product that will shift left. Endothermic heat is a reactant. So adding a reactant to a chemical reaction that's endothermic will shift it to the right towards the products. So it just depends. Just treat the heat like a product, and then you shift. Adding heat, you shift away from that, and if you take heat away, you shift towards whichever side has the heat. So just pretend like it's like a reactant or product, and then apply it in that regards. So and it's still the same thing. So all right, Le Chatelier's principle changing temperature. So adding heat, then you will shift to the right, and you can see this with the NO2. It's a brown gas. And thank you for listening. And we'll continue to talk about equilibrium for the next couple chapters.